I want to talk with you about section 4.6 in our textbook. Oh, we are making such good progress. We're in packet 29. We're going to be talking about sketching graphs today. We've been playing with sketching graphs for quite some time as a class now. And because we've been being like, okay, here's a graph, sketch its derivative, and that kind of stuff. And I think that's really cool. So what we're going to do is we're going to get a bit more explicit, and in fact try to go the other direction this time. Like if you just have the first and second derivatives of a function, can you see what a decent picture of it looks like? Or like how can you get a handle on what a function looks like just by kind of looking at just by looking at the function itself, and not even like you're appealing to tools like computers. So I want to start by refreshing your memory on the first and second derivatives. The first thing that I want to remind you is that the first derivative determines the increasing or decreasing nature of the function itself. So if I draw a function over here on the left-hand side, so this is going to be a picture of f. And then over here, I draw f prime. There are some parts where this function is increasing. So it's increasing there and there. And the function is decreasing from there all the way over to there. Right? So in the case of the parts here, this means that f prime is positive. And in terms of the decreasing sections, that's where f prime is less than 0. Oop, I forgot to write the bigger than 0. Okay? So when I go to sketch these particular places, let me go ahead and mark some important places on the x-axis of this function right here. Let me call them, say, like C1, C2, and C3. And f prime is going to be bigger than 0, less than 0 on the different intervals of that. So let me replicate where C1, C2, and C3 are on my picture of f prime that I'm going to construct right now. Well, in this area of the function right here, the function is increasing, but eventually the function is flat, and that's right here where the derivative takes on value 0. So I'm going to go ahead and be bold and start committing to marks on my paper. So the derivative is going to do something like this, because the derivative is positive, but going to 0. And then in the next interval from C1 to C2, the function is f is decreasing, and its slope starts out at about 0, gets steeper, and then goes back to 0, but f prime is negative that whole time. And so that looks like something about like that, right? F prime negative and f prime positive. I think I want that in peach. And then over the next segment, from C2 to C3, I think my placement of C3 could be a bit better. I think that's not great. I was kind of in the wrong box. I apologize for that. So in this next one, f is increasing, and so the derivative is going to be positive. About like that. And then over the next segment from C3 to infinity, the function is decreasing. And so I'll draw that. The function is decreasing, but the slope kind of levels off. and doesn't get any steeper. And in fact, starts getting less steep. Right, and this is more negative, less negative. Okay, so the second derivative determines whether the function is concave up or concave down. We learned that in section 4.4. So let me copy, I think, no, I'm gonna have to redraw it. There's probably a way for me to just like copy, so I'm gonna try to recreate my same diagram, my same function that I had, because it seemed like it was pretty good. It's not gonna be perfectly the same, and that's okay. All right, let's take that as what it is. And let's not label the same things. We're going to label different things. I'm going to label the concavity, concave up, concave down. So what I'm going to do is I'm going to draw my concavity arrows. Are you starting to like concavity arrows yet? I love concavity arrows. Let's put in the inflection points. Let's call those piece of 1, piece of 2, and piece of 3. All right, so in these different places, from minus infinity to piece of 1, f double prime is less than 0. From piece of 1 to piece of 2, because the arrow points up, the second derivative is positive. In the next interval, from P2 to P3, my function is concave down, which means that the second derivative is less than 0. And then from P3 to infinity, we've got an upward facing concavity arrow, which means that f double prime is bigger than 0. So I'm going to take and replicate the positions of my inflection points. And now we're going to draw a function that's like, it's going to be, let's see here, from negative infinity to piece of 1. We're drawing the second derivative, right? F double prime. We're drawing the second derivative, and I need it to be negative. F double prime is 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 negative. Okay, fine. F double prime is negative. Fine. I was told that I had to do that. Okay, in the next region here, F double prime is positive. F double prime is positive. Then over the next interval, F prime is negative. Sorry, double prime. And then finally, we're going to have a concave up function. F double prime bigger than 0. Right? I'd like to remind you, okay, so let me put some annotation here. This is, F double prime, F just itself. And then above we had F and F prime. So the two on the left here these should be identical plots. All right, going from here to here, I take a derivative, and going from here to here, I take a derivative. Right? So what we should see, if I just focus on these two plots right here, is that the one down here, this is the derivative of that one. So going in this direction here, I take a derivative. And so anywhere that I see this thing is going to have derivative 0, we should have a root right here. Derivative 0, I've got a root there. Derivative 0, yeah, this isn't a great perfect picture. I've got a root right here. I mean, it's really hard to do this perfectly by hand. And then where this function is decreasing, this one down here is negative. Where this one is increasing, this one's positive. where this one's decreasing, this one should be negative. Yep. And then increasing, and this one is positive. So there's a slight discrepancy about that mapping. But whatever. All right. So that's increasing, decreasing, concave up, concave down. So I want to tell you about the building blocks of graphs of differentiable functions. Because we talked entirely in the previous page about increasing, decreasing, concave up, concave down. And I'm going to use those as my 4 basic building blocks. Because if I included another property, I have 8. And 8's starting to be too many for me to know how to just like put together. I could do it, but it'd produce better graphs, but it'd be far more difficult than just using these 2 properties. So there are 4 basic building blocks. I want to use, so let's do that one, and that one, and that one. I think I want to go like that. I think that's a better picture. I forget what I did in my YouTube video about this. Do not expect perfect consistency from me in my different formats. My mind works different ways at different times, and I think that's okay. I bet yours does too. So, let's take a look here. I'm going to divide this like this. The top 2, let's go ahead and letter them, shall we? Let's call this A, B, C, and D. So the top 2 are both increasing functions. And the bottom 2 are both decreasing functions. I might have to swap 2 of these. Yep, I'm going to have to swap them. Aww. Undo. Oh, that's right. I only have to circle any part of it and then I can do it. Oh, look, that's weird. It just leaves behind some garbage. Boop. Give me that. Yeah. Okay. There we go. Now I made a similar error in my YouTube video, and it's useful that I leave those in because it lets you see how I'm categorizing them in my mind to find the right way to order them. So me explicitly leaving those in, I think, is helpful. So I'm going to draw the concavity arrows next. The ones on the left are both concave up, and the ones on the right are both concave down, right? As opposed to increasing, decreasing. Okay. So let's go ahead and label those. These are concave up, concave down. I'm not finding the A, B, C's, and D's useful at all. Right, so we've got these four basic building blocks, and so basically what you're gonna do is we're gonna separate the interval into intervals, and then on each interval we're gonna find which of these 4 basic building blocks are there, right? So you need to know each of the 2 properties. You need to know whether it's increasing or decreasing, and concave up or concave down. No problem. That's when f prime determines increasing, decreasing, and f double prime determines when it's concave up or concave down. So we're going to, just like we were doing for optimization, split intervals based on critical points and possible inflection points. So determine the SIGN signs of f prime and f double prime on each of those intervals, and then use that to solve a problem, in this case, graphing, by grabbing which of these 4 things is it for each of those intervals. There are a couple of additional useful things, like vertical asymptotes. So they can tell me whether I have this or this, right? One of them has an asymptote, a vertical asymptote, and this one has no asymptote. And so having the asymptotes in place helps me know which of those two things is it. And then the stuff at infinity is really helpful because it's like, okay, fine, what's going on here? Should it go up to positive infinity? Should it oscillate? Should it go down? You know, which is it? So I've got a process for you for graphing functions. I did not make a flowchart for this one. So I think you should build information about f prime and f double prime. What do I mean by that? Well, I mean, we need the critical points. We need possible inflection points. I need intervals whose bounds are determined by the critical points and possible inflection points. And then on those things, I need signs of f prime and f double prime on intervals in order to do this. Okay. We're going to draw axes and add transition points. That's what our book is calling critical points and possible inflection points. We should probably throw out the possible inflection points, but because they just add an additional layer of vibration that we don't need. And then sketching asymptotes, cool. Sketching our building blocks, each of our 4 building blocks. And then finally, probably revise our image because it's probably not as good as we want it to be. So let's practice. Let's sketch x squared minus 4x plus 3. Cool. We're going to build information about this. Right? So let's call f equals x squared minus 4x plus 3. Oh, I'm really struggling with the handwriting today. I have a new desk coming, which we should hope solves that problem. Okay, so f prime equals 2x minus 4. And f double prime is equal to 2. Okay. Let's draw some conclusions already based on that. So f double prime equals 2 says that we have no inflection points, and in fact that it's always concave up. F prime equals 2x minus 4, fine. So that means that 0 equals x minus 2, and x equals 2 is crib point. So what I'm going to do is I'm going to draw a number line. I'm going to choose a test point. Let's call that t sub 1, t sub 2. Let's go with 0 because that's really easy, and 3. I don't want those above. 0 and 3. Those are my test points. So f prime at 0 is equal to 2 times 0 minus 4 equals minus 4, which means that f prime is negative. We're determining the increasing, decreasing nature of our function f. Over here on the other side, we're going to have that f prime of 3 is equal to 2 times 3 minus 4 equals 2. It's bigger than 0, f prime bigger than 0. So from that, I can conclude that f is increasing on 2 to infinity and decreasing on minus infinity to 2. And I think that's enough because I've got the basic building blocks. So let's go ahead and draw some axes. So let's do that. I've got this x equals 2 on the x and y axes. Cool. Let's see here. So I know that over here, decreasing and concave up, increasing and concave up. There, because this splits at x equals 2 at that critical point. That's the only point that we add because we didn't have any inflection points. It's because it's a parabola. All right, so we've got decreasing concave up. Decreasing concave up. Here's the decreasings. Concave up, it looks like that. Okie dokie. Decreasing concave up. Increasing concave up. It's a parabola. So I would say probably the next thing that we're going to do is that is not well placed. It's supposed to be to the right of that. There. Not so bad, really. Those parabolas are pretty easy. Let's try this quartic. Quart for form. F equals 3x to the fourth minus 8x cubed plus 6x squared plus 1. Find f prime equals 12x cubed minus 24x squared plus 12x. And I know I'm going to need the second derivative. F double prime equals 36x squared minus 48x plus 12. All right. Just doing a quick mental check of my work. I think it's correct. So this thing is, we're going to generate my crib points. This one's going to generate my inflection points. So let's start by focusing on the computation of the critical points. I don't want to work with all these like 12s and 24s. This sucks. So since we only care about sign, not magnitude, I'm going to work with the division by 12. So I'm going to play with x cubed minus 2x squared plus x, which to me looks so much better because I can totally mentally factor this. This is pretty easy. So that's, that's x times x squared minus 2x plus 1. That's x times x minus 1 times x minus 1. So right now I'm finding the roots of this thing. So this generates x equals 0 or x equals 1 are critical points. One of them is a double root. I've got a double root of x minus 1. And there's a pattern with those we'll see it demonstrated in this particular problem. Okay. So this generates a number line. And what I want to do is I want to find the SIGN sign. I want the sign of f prime on each of these 1, 2, 3 intervals. So I'm going to choose test points. I'm going to go with -1, a half, and 2. Those are going to be my test points. F prime at -1. Again, I'm working with the scaled. So why don't I call f sub s equals x cubed minus f prime s, x cubed minus 2x squared plus x. Because the sign of fs prime is the same as the sign of f prime. Because one is scaled by a positive number of the other. So f prime at -1 is equal to, let's see here, -1 cubed minus 2 times -1 squared plus -1. That's -1 minus 2 minus 1 is less than 0. F prime negative. F sub s prime at a half is a half cubed minus 2 times a half squared plus a half. Eighth minus a half plus a half bigger than 0. And f sub s prime of 2 is 2 cubed minus 2 times 2 squared plus 2 equals 2 is bigger than 0. So all I was doing there was trying to determine the increasing, decreasing nature. I found 2 critical points, 1, 2, 3 intervals. On each of those intervals, I found a test point. I evaluated the derivative at those test points to find the sign of the derivative. I want the sign of f prime because now I know that I've got a decreasing, increasing, increasing function. So decreasing, increasing, increasing. Now I just need to know what's the concavity on each of those 3 intervals. And that's going to come from f double prime with concavity. So let's see here. So let's solve this equation to find my possible inflection points. And so I want to know, I'll do this in green. 0 equals 3x squared minus 4x plus 1. I divide it by 12. Does that seem like a good thing to do? Let's divide by 3. Ooh, I think that 4 thirds minus 4 thirds equals minus 1 minus a third. And I'm pretty sure that a third equals minus 1 times minus a third, so that this factors as x plus 1 times x plus a third. No, how did I get off on those SIGN signs? That was terrible. It's minuses. What are you talking about? Sorry. All right. Are you down with how I factored that? If you don't believe me, why don't you go ahead and you could use a quadratic formula and you'll find these 2 roots. But you could always just FOIL this out and you'll get that thing back. This tells me that I have 2 inflection points. That's a 2. X equals 1 and x equals a third. Neato Frito. So I've got a number line. I've got possible inflection points. 1/3 and 1. And the thing I need to know here is the sign of f double prime. You know what I'm not going to do is work with this thing because I don't want to track those 36s, the 12s around. That sounds terrible. So I'm going to do what I did on the previous one, and I'm going to be like, let's let f sub s double prime equals, I should just call it f sub 2 or something like that. This notation is getting bad. Let's call that 3x squared minus 4x plus 1. Now let's choose some test points. I'm going to choose a test point here of 0. I'm going to choose a test point here of a half. I'm going to choose a test point here of 2. Just using convenient values in the intervals. And I have 1, 2, 3 intervals. 2 points, 3 intervals. So I want to know what is f sub s double prime of 0. That's equal to 1. F sub s double prime of a half is equal to 3 times half squared minus 4 times half plus 1. That's 3 over 4 minus 2 plus 1. 3/4 minus 1 is minus 1/4, which is less than 0. We'll use our third test point. It's 3 times 2 squared minus 4 times 2 plus 1. 12 minus 8 plus 1, that's bigger than 0. So I know that f double prime here is, let's see here, bigger than 0. F double prime is less than 0. F double prime is bigger than 0. Concave up, concave down, concave up. Let us now draw some axes. I'm not going to draw the vertical axis until I draw the horizontal axis. And what I'm going to do is I'm going to add my inflection points and I'm going to add my critical points. And those are going to show me the intervals for which I need to sketch in little pieces of this. It's a cortex. It probably has 3 little humpy humps, 2 valleys, and 2 valleys and a hill. All right, so let's add 0 and 1. Those are my critical points. And how about I do in green a third and 1. And those are my inflection points. Okay, so I have 1, 2, 3, 4 intervals. For each of the intervals, what I want to do is I'm going to go find whether it's increasing, decreasing, concave up, concave down. And so let's take some notes. Let's see here. So from infinity to 0, my function is, looks like it's decreasing because f prime is less than 0. Decreasing. And what's the concavity? Well, we'll go do a lookup over here. It's that part right there. It's concave up. Decreasing, concave up. From 0 to a third. From 0 to a third, f prime is bigger than 0. We've got increasing. From a third to 1, I've got increasing. From 1 to infinity, increasing. From 0 to a third, let's look up its concavity value. From 0 to a third, concave, looks like concave up. On the next interval, from a third to 1, concave down. On the last interval, from 1 to infinity, concave up. All right, so now I have the decreasing, increasing, concave up, concave down behavior of my function. So I need to draw a decreasing concave up, increasing concave up, increasing concave down, increasing concave up. And this is why I say now we'll revise, because now I have a pretty good idea of what this thing looks like. So let's go ahead and draw some axes again. If you want to fix the vertical position of this function, then you could like sample a point. Like at 0, it passes through 1. Okay, cool. So I know it has to pass through right here. And all I did to know that it passed through that point is plug in x equals 0. And now that fixed that. I knew that there weren't any asymptotes because it's a polynomial. Okay. So let's do our best. I know that 0 to a third, to 1 to infinity. Feel free to compare with your calculator. I love this. This is so fun. So I have 2 more of these left. If you're not into it, then or you feel like you've got good mastery, by all means, stop. I don't know. I kind of want to just like relegate this one to discussion in the book. So the only thing that makes this one different is that it's from 0 to pi. So this is over some particular interval. So when I'm constructing my number lines, I'm just going to pay attention to only the crit points and the inflection points in this interval. That's the only thing that really makes this example special. And our book does have a good, thorough discussion of this example. And so I think in the interest of time, I'm going to pass on this one. If you want me to, you can always bring this up in lecture. Not lecture, but our class discussions, and we can talk about it then. So I'm gonna give this one a pass and say, see the book. It's in section 4.6. So let's pass on that problem and do this last one here. This one's basically going to be about the same. The big thing here is that I've got this division by, and then I've got this thing down here, which is going to lead to an asymptote. So that's kind of what's going to make this problem special. So asymptotes are going to be where the denominator equals 0, and the numerator doesn't. Otherwise, I always have a common root, and I'm going to do something else to figure it out. So looking at where the denominator is 0, that's where 0 equals 2x minus 4. That's where x equals 2. So that means that I have a vertical asymptote at x equals 2. Now the question is, does it look like that? Does it look like that? Does it look like that? Nope, I already had that one. Does it look like boop, boop, or does it look like that? Which one of these is it? Or the asymptote? So which one of these is it? Well, let's figure that out. We could answer this question by taking the limit as x approaches 0, or x approaches 2, that's where asymptote is, of 3x plus 2 over 2x minus 4. I know I have 0, sorry, I don't have 0, 0. I feel like I'm not doing very well at this. That's where I have 3 times 2 plus 2 over 0, 8 over 0. And now the question is, the SIGN sign of this is determined by the sign of that 0 there. So we need to know the limit as x approaches 2 from the right, and the limit as x approaches 2 from the left of 3x plus 2 over 2x minus 4. And now I'm going to play some tricks. And I hope that you appreciate this. So I'm going to try plugging it in, and I'm going to have 3 times 2 plus 2 over 2 times 2 plus minus 4. And that's 8 over 4 plus minus 4. Well, that 4 plus is a little bit bigger than that other 4. And so this is equal to 8 over positive 0, positive infinity. All right, check this out. I think this is so fun, okay? So let's try doing that again. 3 times 2 minus, not minus 1. Come on, brain. 2 from the left plus 2 over 2 times 2 from the left minus 4. And the top I still have 8, and it doesn't matter whether it's going from above or below. In this case, it'd be below. It is, in fact, 8 minus, if you care. And then I have 4 minus 4, but this 4 right here is a little smaller than that other one, and so the sign of this one is negative, and so that means that this is equal to 8 over negative 0, which is equal to negative infinity. We have now selected the type that it is. It's from the right. From the right, it's positive infinity, and from the left, it's negative infinity. From the left, it's negative infinity. From the right, it's positive. It's this one. Around 2. Isn't that process cool? I love calculus so much. Wow. Oh, calculus. Oh, you're so amazing, calculus. I see another thing we could play with here. I know that the function has a root at x equals minus 2/3. Because if I plug in minus 2/3 to this thing right here, the 3's are going to cancel, and I'll be left with minus 2, and then I'll have minus 2 plus 2, and I'll have 0. So I've got a root at minus 2/3. That's kind of neat. Let's play with the increasing, decreasing nature of this function, shall we? So we're going to have to play with the first derivative. So f prime is equal to 2x minus 4 times 3 minus 3x plus 2 times 2 over 2x minus 4 squared. Low, high, minus high, low, draw a line, is curve below. Okay, so checking out this thing right here, it looks like I'm going to have a critical point at x equals 2, but no, 2 is not in the domain of my function f, so 2 is not a critical point. And that's more or less because this. So we're just going to think about the numerator. F prime equals 0. That's when 2x minus 4 times 3 minus 3x plus 2 times 2 equals 0. Let's do that distribution. 6x minus 12 minus 6x plus 4. Being careful with the SIGN signs here, yo. I'm a little concerned that I'm about to get 0 equals. Let me think for a second. Yeah, okay. I mean, I'm just letting the arithmetic do what it does. Low D high minus high D low. Draw a line and square below. We're dealing with the numerator. I correctly distributed the 3 across the 2 and the 4. Those minuses, that's fine. You know, that's fine. We're just doing simplification. Maybe you would argue that we would have done simplification back here before we started playing this nonsense, but like, you know, whatever. We'll let the 6x's cancel. Hmm. 0 equals minus 16. That means there's no crit points. That's okay. That's because this is equal to minus 16 over 2x plus 4 squared. That's a minus. So that's all we found. The numerator can't possibly be 0. Fine. So we have no critical points. Well, I still have this divide at the asymptote 2. And we should probably play with the concavity here also. Let's play with concavity. I need f double prime. There's single derivative, double derivative. I'm not ready for that. I want to simplify. I'm including my thought process here. Like I could do this all ahead of time and not have to think and show you steps and like stuff like that. But I think it's important that you hear my thought process as I do this, right? Like I don't just know the answers. I make mistakes along the way all the time, and it's important that you see that. So I'm going to write this as minus 16 over 4 times x minus 2. And that's because that 4 is 2 squared. So what I did there was I took the common 2 here, I pulled it out, and I've got a square on it. I'm missing a squared. And let's cancel some stuff. So that's going to be minus 4 over x minus 2 squared. Okay, I just didn't want to deal with a bunch of stuff when I take the second derivative. So that's f prime. F double prime is equal to... I'm just going to use the chain rule with the power rule, and we'll find that this is equal to 8 over x minus 2 cubed. Yep. There's a minus 2 right here, and the power rule changes those signs. This is the same thing that f prime did in terms of its possible inflection points. Only possible one at x equals 2, but there's it's not in the domain. So basically what we found between those two calculations for the critical points and the possible inflection points is that when I go and draw a number line here, it's going to split it 2, and what's going on the two sides of it is all. That's it. That's the only thing there is. I've got an asymptote right there. So I just need to know what is the SIGN sign of f prime to the left of 2 at 0. So if I plug in 0 to f prime, I have minus 4 over minus 2 squared. That's less than 0. So it's decreasing. And sine of f prime at, say, 3 is minus 4 times over minus 3 squared. What am I saying? Minus 3 squared. That's nonsense. Positive 3. Where am I looking? I'm looking here. 3 minus 2 squared. Well, whatever. That's going to be less than 0. Decreasing. What about the concavity, yo? What about the concavity? To determine the concavity, I'm going to check out the sign of f double prime at 0 and the sign of f double prime at 3. Were this 0 and 3, you might be like, where did those come from? Those are just 0 and 3, my arbitrary test points that I'm plugging in to determine the decreasing or increasing concave up or concave down behavior of my function on either side of the asymptote at 2. Okay? So I'm going to take 0 and I'm going to plug it into my expression for f double prime. 8 over minus 2 cubed is less than 0, so that means it's concave up. And then if I plug in 3, I'm going to have 8 over 1 cubed. That's positive. I think, oh, no, I made a transcription error. Nope. It's so easy to do that. That's down because the first one was negative. 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 Whoo-wee. Okay, so we're focusing on that section of the screen now. I happen to know that my function is decreasing concave down, that I've got a vertical asymptote right here. We determined earlier that it's going to look like that. Oh my god, it really is. It's going to be decreasing concave down. Look at this. Look, it's concave down, decreasing concave down. Okay, the function that I'm after really does look like that. It's decreasing concave down. Didn't we find a root earlier? Minus 2/3? Right there. There's minus 2/3. Decreasing concave down, decreasing concave down, decreasing concave down. Root at minus 2/3. Decreasing concave down. Decreasing concave up. Whoop. And there's probably a horizontal asymptote here too. And I don't have the energy to find it right now. We could take the limit as x goes to infinity in either direction for this function. To the left, it's going to be 2/3, and to the right, it's going to be 2/3. So I just used leading behavior on that part up there. So I can do better. I can do better. I said I wasn't going to do it, but then I was like, you know what? I can, and I'm going to do it. I know that the height of that is 2/3 because I looked at the leading behavior of my function. Ab infinity, a skill I learned in chapter 2 because I paid close attention and thought it was fun. Okay, It's time to take a break and see you again for our final lecture for chapter 4 before we move into integration. Bye.